We can see your screen.
Okay. Can I start?
Go
Okay.
ahead.
Thank you very much. Kind introduction, Dr. Berg. It is my great pleasure and honor to have my talk for European biggest projects, 2030 plus. So my name is Shinichi Komaba, and I am in Tokyo now. So my time is now 11:30 p.m. During my talk, I will see tomorrow. And I think for European people, I should say good afternoon. So today I would like to describe and to introduce of our past research work of potassium and sodium ion chemistry for sustainable battery. So first, when we look at the periodic table, group 1, they are very important element for electrochemical energy storage. Hydrogen is important for not only nickel metal hydride, but also fuel cell. Lithium, of course, lithium ion. Sodium ion, potassium ion as the alternative post-lithium ion batteries. And recently, we are also focusing on very new electrochemistry, like rubidium electrochemistry, but it is not for practical battery. So in the periodic table, we have many choices of metal ions and also ionic carriers. But in my personal opinion, from lithium to potassium, these three alkaline metals are very advantageous for battery energy storage system. So when we compare the ionic size, of course, lithium is smallest among the alkaline metal ions. However, by dissolving lithium, sodium, potassium, and rubidium ion dissolved in some liquid electrolyte, then the plus cation have chromic interaction with polar organic solvent or water molecule. Then in case of propylene carbonate, we see some Stokes radius. This is the size of solvation shell. Of course, in case of water aqueous solution, we have a Stokes radius of the each alkali ions with hydration shell. As you can see here, in case of magnesium and aluminum ions, the solvation shell are much larger than alkali metals. On the other hand, in case of lithium, it's biggest, showing biggest Stokes radius, radii compared to sodium and potassium. And this alkali metal, we have smallest Stokes radius for rubidium. In case of potassium rubidium, it is surprising that the Stokes radii is smaller than crystalline ionic size, because such kind of large alkali metal can destroy the water or solvent chromic interaction network. Then the Stokes radii should be smaller than exact ionic size in solid ionic compound. Anyway, because of the smaller Stokes size due to the weaker chromic interaction, then we will see some very unique electrochemistry and also ionic devices. In particular, when we compare lithium, sodium, and potassium, of course, the atomic weight, atomic mass should be heavier than lithium for sodium and potassium. It is quite disadvantageous. However, in case of E0, standard electrode potential is lower the potassium case is lower than lithium. This means that wider potential window can be achieved for potassium system. And also, as I mentioned, Stokes radii should be smaller for sodium and potassium compared to lithium. And ionic conductivity, that is, limiting molar ionic conductivity in the propylene carbonate, is higher for potassium and sodium than lithium. Dissolution energy, especially at the interface dissolution process, should be much low barrier for sodium and potassium compared to lithium. Melting point. Yes, lithium is the highest among these alkaline metals. Generally, metallic sodium and metallic potassium are quite reactive with water, but when we assume that dendrite formation inside the battery during overcharge, then we will have internal short circuit between positive and negative electrode through dendrite. But after heat generation, because of melting point for potassium should be lower than sodium and also lithium, then Joule heating will melt down the dendrite short circuit for potassium. This consideration, we expect that sodium and potassium dendrite will be fused by Joule heat. Then we can reasonably believe that better safety compared to lithium overcharge condition. So not only alkaline metals comparison, we are already utilizing potassium ion in practical dry cell, such as manganese dry cell and nickel metal hydride. Maybe today all of the audiences are battery experts, and everybody knows that 6 mol per liter potassium hydroxide aqueous solution is used for alkaline batteries because potassium ion, hydrolyzed ion size is smallest for potassium, mobility as charge carrier, faster mobility for potassium than sodium and lithium. So finally, ionic conductivity is the highest for potassium hydroxide aqueous solution. So that in order to decrease, in order to minimize the internal battery resistance, potassium hydroxide is the best choice for alkaline batteries. So from the aqueous to non-aqueous, then we can use alkaline metals as electrode material. So in this paper from the Professor Compton's group, they reported the electrode potential of group 1 alkaline metals in the ionic liquid, like lithium, sodium, potassium, rubidium, and cesium. If all of potentials are referred to lithium positive E0, then lithium is here. And depending on solvent and solution condition, the E0 can be changed. In case of sodium, basically the E0 is higher than lithium. But in case of propylene carbonate, potassium and rubidium deposition potential is lower than lithium. But we note that any electrochemistry and physical chemistry book, always E0 value is referred to aqueous solution, H2O, then lithium is believed to be lowest E0 in the any periodic table elements. But actually, in case of typical battery electrode like propylene carbonate, the E0 is sometimes lower than lithium. So we tested by ourselves after electrochemical decomposition, electrochemical plating for sodium, lithium, potassium, rubidium. Then we compared open circuit potential for 24 hours. On the copper foil, the sodium deposition equilibrium potential is higher than lithium, but lower for sodium and rubidium case. So we note that potential window is wider for sodium and rubidium case if we reasonably assume that the anodic limit is same. I mean, anodic limit is determined by the solvent species. So when we take care for, when we use sodium, potassium, rubidium as the electrode, I mean, metallic sodium, potassium, rubidium, we should make sure to handle these metals safely because they are highly reactive than lithium, of course, and also melting point is lower than lithium. This means after heat generation reaction, potassium, sodium, and rubidium are very, very dangerous. So today, I will introduce first rubidium recent achievement in our lab, and then I will mention about sodium and potassium battery application. And first, let me show you the rubidium cell, rubidium GIC, and the layered rubidium oxide. So look at this slide. Well, the chemical synthesis of stage 1, stage 2, and stage 3 graphite interconnection compound, and also potassium rubidium cesium, GICs, are reported very, very long time ago. And in case of electrochemistry, of course, lithium was already reported more than 40 years. In case of sodium, it is very unfortunate that sodium cannot integrate into graphite. But potassium, rubidium, cesium can integrate not only chemical but also electrochemical reaction. This means that potassium is larger than lithium, but the larger size of sodium is not reason for no integration, no intercurrents, because larger potassium, rubidium, cesium can integrate into graphite with very high reversibility. And we recently achieved the reversible electrochemical integration of rubidium into the graphite. The data is here. In case of lithium, as you can see here, the reversible capacity is approaching to 400, corresponding to lithium 6 stage 1 compound. In case of potassium and rubidium, stage 1 compound corresponding to KC8 or rubidium C8, then reversible capacity is about 280 milliampere hours. In case of sodium, as I already mentioned, that the electrochemical reactivity is negligible for graphite electrode in aqueous sodium cell. So the best choice is hard carbon for practical sodium-ion battery. Anyway, rubidium GIC shows highly reversible insertion and extraction in non-aqueous ionic liquid system. Very recently, we also studied, we reported also alkali rhodium lead oxide and potassium and cobalt rhodium and iridium electrochemistry. In the periodic table, the combination of group 1 and group 9 cobalt elements, then we have layered oxide. And in case of rubidium and rhodium case, we can synthesize the layered oxide having a P2 layered structure and electrochemistry is here. So as you can see here, very beautiful charge-discharge curve in rubidium half cell, but the reversible capacity is so limited. So this means that by combining graphite and rhodium oxide, we can assemble rubidium-ion battery. But please note that there is nothing sustainable, no energy storage, less energy storage, and not attractive for practical use, but I believe unique. in terms of science. So anyway, not only rubidium, but also because of importance for practical use and sustainable battery technology, potassium and sodium case are very attractive compared to lithium. Because when we look at the elemental abundance in the Earth's crust, lithium, copper, and cobalt, all of them are so limited in the Earth's crust. But if we shift to sodium and potassium ion, we do not need copper, cobalt, and lithium at all. Then we will have very sustainable battery based on sodium and potassium intercalation chemistry. So we already published two very heavy review paper in chemical reviews for sodium and also potassium ion. As I already mentioned that the atomic weight is heavier than lithium. However, diffusion rate, the mobility of potassium and sodium ion should be faster than lithium. And also the working potential, working voltage of the battery should be comparable to lithium. In 2009, by combining nickel manganese oxide and hard carbon, that is disordered carbon, and by using the non-aqueous sodium ion electrolyte solution, we demonstrated 3 volts charge discharge battery. At that time, 2009, nobody believed that the SEI formation on the negative electrode and also high reversibility of sodium intercalation into layered sodium oxide. So in our paper 2011, we mentioned that the important experimental condition for electrolyte and hard carbon. I mean that water contamination into the electrolyte solution is very, very important. Then we carefully optimize them. Finally, the dew point must be quite low in glove box. And also we should carefully choose the electrolyte quality. And finally, we conclude that the Kishida Chemical Corporation's battery grade electrolyte solution is best choice for sodium insertion electrochemistry. And for hard carbon, after careful comparison, we selected hard carbon from Kureha Chemical Corporation. Then we succeeded in demonstrating highly reversible sodium insertion and extraction, not only carbon, but also layered oxide. We demonstrated this reversible sodium ion cell. And about 20 years earlier, Sony reported that first lithium ion cell based on cobalt and graphite or hard carbon. It was very, very surprising that 3 years earlier, the patent filed by Showa Denko, Hitachi, and Allied Signal Corporation reporting that the P2 type sodium cobalt oxide and the mixture of lead, metal lead, and polyparaffin conducting polymer mixture shows highly stable sodium ion charge discharge property. But we need cobalt, and also the negative electrode is so highly different from simple carbon material. So, but recently the sodium ion battery is expected as host lithium ion because of we need only abundant metals for sodium ion application. And one Chinese company announced that the launching sodium ion in this year, already it was launched. And also 2 years ago skyrocketing lithium carbonate price. And we are now many researchers trying to find out which is the best choice as beyond lithium ion, like solid state lithium sulfur, lithium ion, and so on. And 2013 sodium battery conference was initiated by Spanish group. This is how to say, this slide showing our first international conference of sodium battery series since 2013. It is initiated by Professor Rojo in CIC Institute, Spain, first sodium ion battery. And it was very great, my pleasure to deliver a lead talk in this symposium. This was 2013, and then after 2013, the number of papers each year drastically increased. And last year, we have many publications approaching to 2,000 publications on sodium electrode and also electrolyte material. And from 2013, we have already 8 conferences on sodium ion battery. First one, Professor Rojo, and the next one, Dr. Johnson, Professor Forsyth, and me for 4th edition, and Dr. Krogneck and Johnson, and Margaret and Stefano. And last year, we had a sodium ion conference in China, organized by Yongxin Hu. And the conference is very successful. One of the snapshot is here. During my talk, almost 500 people are listening. This is very surprising because first time sodium ion battery conference audiences are less than 100, but now huge community are interested in the future of sodium ion battery. And some of the information showing that not only Chinese company, but UK, France, US, and Swedish company focusing on the practical sodium ion battery for future energy storage system. So from now, I will mention the details of each material for sodium and the potassium ion battery. First, let me show you the hard carbon negative electrode. So 2000, Professor Jeff Dunn reporting that hard carbon electrode in sodium cell. Reversible capacity is higher, approaching to 300, but the cycle life is so limited. So in this paper, only 3 charge-discharge curves are shown here. And graphite do not accept sodium ion through electrochemical reaction. So based on this very pioneering paper, we try to optimize the interface perturbation, electrolyte additive, binder, sodium salt, solvent, and additive. And one of the examples is binder is very, very important. And it is very fortunate that we reported that 3 different binders for lithium-ion battery. And by using these binders for hard carbon electrode in sodium cell, you can see here polyacrylate and carboxyl methyl cellulose are best choice compared to PVDF. The capacity degradation for the only PVDF is due to the defluorination caused by incomplete SAF formation on the surface of hard carbon. In case of fluorine-free binders, as you can see here, it is quite effective to improve the cycle performance for hard carbon electrode. Because of the binder success, we can stabilize the electrochemical sodium insertion and extraction. Then we can open the new field for sodium insertion mechanism study. So after sodiation of hydrocarbon through electrochemical reaction, we carried out many different strong analytical tools like X-ray and small angle diffraction, NMR, muon neutron computation, and so on. And our conclusion is to the first, the higher potential region, higher than 0.15, the sodium can integrate into the stacked graphene layers, carbon layers. And the layer potential region, the sodium can move into the nanopore, then sodium pore filling mechanism also active for electrochemical reaction. So based on such kind of insertion mechanism understanding, we can extend our study to synthesize higher capacity hydrocarbon since 2009. So first, the hydrocarbon was kindly supplied by Kuriha Corporation, and we achieved 260 milliampere hours. But recently, we succeeded in much higher capacity of 480 milliampere hours by changing the synthesis method to improve the hydrocarbon nanostructure. The paper is here. Magnesium oxide template synthesis is a very efficient way to improve the reversible capacity of hydrocarbon. Please note that first author is the Azusa Kamiyama, who was the not PhD, master course student in my lab. She contributed the high capacity electrode material preparation. So preparation route is here. You see, the starting material is not only glucose, but it was mixed with magnesium gluconate, then freeze dried to make sure the atomic scale, the homogeneous mixture, then heat treatment at intermediate, and then finally carbonization to have hydrocarbon. Because of magnesium containing starting material, after the heat treatment, we have not only the carbon matrix, but also highly dispersed magnesium oxide in the carbon network. And during post-heat treatment at 1500 degrees C, during this heat treatment, magnesium oxide must be reduced first. Then MgO is translated to Mg metal. But boiling point of magnesium metal is 1100 degrees Celsius, so that magnesium is easily evaporated and vaporized. Then after vaporization of magnesium metal, we have nano-sized pores in the hydrocarbon. So this means that magnesium oxide is acting as template for nanopore formation. So actually, from the TEM observation, freeze drying successful method, from a dark field image, we can see that very small particles are well dispersed in the carbon matrix. This is direct evidence the formation of magnesium oxide nanocrystals in hydrocarbon. The size is about 1 or 2 or a few nanometers in diameter. So after post-heat treatment, we can remove these magnesium oxide, then reversible capacity is here. So compared to Kuriha's hydrocarbon and sucrose, argon, cellulose, and phenol resin-derived hydrocarbons, this templated hydrocarbon shows extremely high capacity, approaching to 500 milliampere hours. So hard carbon shows high capacity, reversible capacity. Next, our concern is safety. So my collaborator, Professor Kazuma Goto, he checked sodium deposition property from operando NMR for hard carbon sodium half cell. So compared to lithium hard carbon system, as you can see here, this one showing charge and overcharge hard carbon electrode, point A, B, C, and D. Dendrite formation can be started from point D. And even in case of overcharging by applying the lower potential than zero of the sodium lead standard potential, then because of buffering effect of the sodium deposition, no dendrite formation. This means that higher safety than lithium can be achieved for hard carbon electrode in sodium-ion cell. And recently, we are also studying on sodium diffusivity in the hard carbon, and we applied mu positive muon spin rotation and relaxation to analyze the sodium diffusivity in hard carbon. And a very recent paper collaboration with Korean group, Professor Myung, who was a PhD student when I was assistant professor in Iwate University, Japan. Now, Professor Myung is now very active researcher for sodium and lithium battery materials. He recently reported that tracking sodium cluster dynamics in hard carbon. So initial stage of sodium insertion, sodium goes into the stacked carbon layers. But by applying lower potential, then this intercalated potassium can gathering and pore filling in the interstitial nanopores. So this process can be believed that sodium can diffuse not only across SCI, but also in order to approaching nanopore pore filling mechanism, sodium can move through the stacked carbon layers. So based on this consideration, sodium diffusivity was evaluated through impedance and also as an additional technique. You can see details in this paper. Anyway, next, let me move on the positive electrode, the layered oxide. In very old paper 1980, Professor Agenmiller and also Dr. Delmas group reported that layered sodium cobalt oxide showing highly reversible sodium insertion extraction. But because of low purity of non-aqueous electrolyte solution, the upper cutoff voltage is just 3.5 volts. Because of limited potential region, then reversible capacity is so limited. But please note that this is first pioneering report of 3 volts sodium cobalt oxide, layered oxide. About 20 years ago, when I was 32 years old, I was a postdoc in France, Dr. Delmas group. I had the opportunity to discuss why layered sodium oxide was earlier reported, but now lithium-ion battery is so active among the battery community. He said that at that time, 1980, nobody believed that 4-volt battery operation because of electrolyte decomposition, which is caused by impurity in the organic electrolyte solution. Additionally, Dr. Delma said to me that you should know that multiple phase transition of layered sodium oxide, which is different situation from sodium and lithium, And such phase transition is very serious problem for practical use because during charge discharge, drastic lattice parameter change, then cracking and collapse of the active material. After finishing my postdoc period, I came back to Japan and I met one very impressive talk in Battery Symposium in Japan 2004. This was the contribution from Professor Okada's group. At that time, some of researchers reporting on lithium FeO2. Its crystal structure is analog, same as lithium cobalt oxide. But in lithium iron oxide, iron 3 plus 4 plus redox reaction is completely inactive, or very difficult to oxidize into 4 plus iron. But by replacing lithium with sodium, such kind of electrochemical reaction is highly reactive and only one plateau, not multiple potential reaction. And iron 3-4 redox couple is highly reversible. And the potential is 3.3 volts. I was very surprised during this oral talk. And then it is fortunate that I got the faculty position in new university, that is Tokyo University of Science, the present current my lab. Then I started the sodium ion research work in 2005. And the first trial was nickel manganese oxide and chromium oxide. And it was reported in Hawaii, a prime meeting to 2008. I had a poster talk, and this is in the front of a poster. I take picture with one postdoc from US. He's postdoc researcher from Professor Whitaker lab. Because I and he, just only two posters, two speakers reporting sodium ion battery. This is my good memory to have the find colleague, my friend for sodium ion battery. But please note that almost nobody visited my poster. Anyway, now sodium ion is very attractive and for layered oxide, because larger size than lithium sodium, then we have not only O3 type layered oxide, same as lithium, but also P2 type, which is not possible for lithium case. So in case of sodium, we have both O3 and P2 type different polytypes. Then we can have very wide variety of crystal structure and also wide variety of transition metals to crystallize the sodium layered oxide. From scandium to nickel, we have O3 type structure and P-type stacking always observed for sodium and potassium, but never observed for lithium case. So because of wide and rich chemistry for sodium layered oxide, we can compare for all 3D elements for O3 type stacking, and also chromium case and cobalt case, we can compare lithium, sodium, and potassium chemistry using the same structure, same crystal structure. So first, this slide showing that the sodium layered oxide from sodium, cobalt, chromium, manganese, and nickel. Because of no electron in 3D orbital, of course, scandium showing less capacity. But recently, these scandium doping have been reported by some researchers, and it is sometimes quite effective to improve the manganese-based layered oxide. Chromium, yes, it is highly active. Manganese and cobalt reversible capacity is relatively high compared to other transition metals. In case of iron, the reversibility limited, but the plateau located at 3.3 volts, which is relatively higher compared to other cases. In case of nickel and cobalt, as you can see here, multi-step potential variation, showing that many different phase transitions, and this should be very disadvantageous for long lifetime sodium-ion battery. So how about cobalt for lithium, sodium, potassium? So lithium is showing lithium case higher reversible capacity and also moderately high voltages, which is compatible for carbonate ester-based organic solution. In case of sodium, the reversible potential should be lower and potassium much slopey and limited capacity. But please note that if we extract all of lithium, sodium, and potassium, finally we will have cobalt dioxide, which is free from alkali metals. Then if cobalt O2, all of them showing around 5 volts because of the same electronic condition after fully extracted lithium, sodium, and potassium. Not only cobalt, we can also compare chromium case for lithium and sodium. It was so surprising that lithium chromium oxide, the reversible capacity is negligible, but in case of sodium, highly reversible at around in the region of 3 volts. So this message is that even in case of electrochemically inactive element in lithium, we should test in the similar sodium cases. Then we expect that very different chemistry, different from lithium chemistry. In case of sodium chromium oxide, several years later, Professor Jeff Dunn reporting that lithium cobalt chromium oxide is fundamentally safe positive electrode because from their thermal analysis compared to lithium extracted cobalt oxide and FePO4, heat generation is much, much lower for sodium chromium oxide. This is very good news for the safety of the sodium-ion battery. So next one is manganese lead oxide. Because of Ian-Terra distortion, sometimes in the previous report showing that also rhombic, that is distorted pit structure named O sodium 2/3 manganese oxide. On the other hand, some of the previous reports that no Ian-Terra distortion, then hexagonal P2 type structure can be found. Always these two phases are mixed, but almost no report to pure phase synthesis. So we tried to have pure orthorhombic and hexagonal sodium manganese lead oxide. The point is here. In case of the 1050 degrees Celsius, we have quite nice orthorhombic distorted pit type structure. But after this post-heat treatment, through additional low temperature heat treatment, because of oxygen uptake, then causes the defect of manganese and sodium side, then we have 10% vacancy for manganese side. Then less amount of trivalent manganese, then distortion this manganese cooperative distortion is disappeared for this lead oxide. So how about the crystal structure here? Because of 10% vacancy, no long-range ordering, But in case of no defects for manganese site, then manganese 3 plus and 4 plus long-range ordering like honeycomb structure stabilize this crystal structure. Then this orthodynamic distorted Yantra cooperation effect also stabilize electrochemical reaction during more than 10 cycles. The higher capacity can be maintained. On the other hand, in case of defective hexagonal phase, capacity decrease and also limited capacity compared to the orthorhombic phase. Because of the wide variety of crystal structure, we can also achieve that very different composition for the 3 plus trivalent transition metal and also mean oxidation number 3.33 for P2 type structure. And from this table, you see that rich chemistry is existing for sodium layered oxide. So one of the typical example is layered iron manganese oxide based on 3 plus 4 plus redox couple for both manganese and iron. Then highly reversible capacity can be achieved in sodium half cell. And also cobalt is not a good choice, but if we synthesize the 1 by 1 layered sodium cobalt oxide, the particle shape, highly crystallite size, and also electrochemical reaction is so excellent. I mean that high rate of capability and also higher reversible capacity and very smooth potential variation during sodium extraction and insertion. Because such smooth potential variation, we also checked the ordering structure from X-ray and also neutron. We have no evidence of long-range ordering of iron cobalt 1 by 1 system. No ordering, no superstructure. But 1 by 1 sodium vacancy ordering was evidence from X-ray diffraction, sodium vacancy ordering. So this crystal structure feature is believed to be advantageous for highly reversible sodium insertion and extraction. And one of typical and for good choice, good candidate for practical use is the iron nickel manganese layered oxide. The below 4 volt potential region, relatively high reversible capacity and also smooth charge-discharge reaction. And because of the iron manganese-based material, it is considered to be one of the earth abundant material for sodium-ion battery. And recently we tried to optimize the nickel manganese iron titanium layered oxide, and finally from this triangle, the phase diagram, this point should be optimal for reversibility and also working potential region. In the next plot, this case, manganese-free composition, it is surprisingly bad. Very, very fast discharge capacity decay. So compositional optimization is very effective. And recently we are trying to apply data-driven computational study to find out new material based on nickel manganese iron titanium system. Anyway, based on this optimization, we try to assemble fuel cell. This hard carbon is very, very high activity, not only sodium insertion, but also potassium insertion. But by using hard carbon and nickel metal manganese titanium system, you can see here 3 volt charge discharge operation can be achieved. And this sodium ion cell, the energy density 312 watt-hours can be achieved, which is comparable to lithium iron phosphate type lithium ion battery energy density. So I believe that sodium ion battery should be attractive as post and low cost secondary alternative battery to lithium ion battery. So next topic is potassium ion. The standard redox potential of potassium is lower than lithium. Look at this picture. If we assume that potential window limited by plating and also anodic limit, which is due to the decomposition, electrochemical anodic decomposition of the organic solvent, then we can assume that sodium and potassium case same anodic limit. In case sodium, because higher E0 of sodium deposition, then a little bit narrow potential window for sodium. However, in case of potassium, because of lower potassium plating potential, then we will see widest potential window compared to lithium. This is very, very good news to have higher voltage battery based on potassium ion system. So in our recent study, one of the best combination as positive and negative electrodes are manganese, hexacyanoferrite, and graphite electrode respectively. Based on half cell test, we can reasonably expect that higher energy density. And this energy density is comparable to some of lithium ion system. Because of attractive energy density and also potential window for potassium ion battery, and the number of scientific papers per year is drastically increasing now. And I believe that 5 years, 10 years later, the potassium ion chemistry should be same situation as sodium ion publication number. We have already the review paper in chemical reviews. The first paper, Tomooki, who was a PhD student in my lab, and now he's in Sweden, Professor Johansson's lab as a postdoc. And he wrote main part of this paper, and total page number is 108 pages. It is so tough work, mainly achieved by Tomooki. So negative electrode, graphite is best choice. Then after careful investigation of binary chemistry and interface chemistry, and also we can use aluminum foil as current collector, then highly reversible potassium insertion and extraction reversible capacity is over 250 milliampere hours, and the stage 1 KC8 is formed after full recharging. From operando X-ray diffraction, we already reporting details of insertion mechanism. And please note that during the potassium intercalation, Domas error models can be applied for this intercalation model similar to lithium case. So maybe I have 2 or 3 minutes. The last part is positive electrode and the electrolyte for sodium and potassium battery. So positive electrode, in order to achieve higher energy density, and which should be comparable to lithium ion, we should have higher reversible capacity and moderately high voltage. Then we will have higher energy density. And one of the present best choice is Prussian blues based on manganese and iron. As you can see here, the iron-based Prussian blue showing 2 voltage plateau at around 4 and 3.3 volts. But by replacing iron with manganese, we can maximize the energy density. And not only plus-assembly open structure, we have some good positive electrode based on polyanions, potassium containing iron or manganese compound. And not only polyanion, metal organic framework should be advantageous for potassium integration because its ionic size is larger than sodium. Electrolyte solution is another issue. So during Homo-Oki PhD period, he mainly contributed to find new electrolyte solution, not only carbonate ester, but also grime, ionic liquid, and the Si formation additive, and polymer electrolyte to achieve all solid state sodium and potassium ion battery. So electrolyte additive, by adding 1% DMSF, then by mixing PF6 and FSA anion, capacity retention is highly robust, highly improved, and during 500 cycles, capacity is almost maintained constant. Less and less capacity degradation by adding small portion of DMSF. So because the cell configuration is just same as lithium ion, then identical manufacturing plant will be adapted for sodium and potassium ion battery. Solid state battery, so basically lithium ion technology can be applied for sodium and potassium case. And another point is no alloy formation between aluminum and sodium, aluminum and potassium, then bipolar cell. Bipolar aluminum current collector can be applied, which is different from lithium case because the lithium case, aluminum and copper foil should be stacked to avoid lithium aluminum alloying formation. And 2 years ago, we also reported all solid state potassium polymer batteries based on platinum blue and graphite, sandwiching the solid polymer electrolyte based on polyethylene oxide polymer membrane. So let me conclude my talk. As sustainable battery, sodium and potassium is one of the best candidates. So systematic study is leading us toward new sustainable material and reaction, and the new generation battery technology as sustainable energy storage will be achieved based on sodium and potassium ion chemistry. So some of the works was supported by some projects, DXGM and GTEx, and this is group photo of my laboratory. So thank you very much for your kind introduction.